LB. So similarly, we define this relation. It's a left translation. We define left translation dually by choosing similarly. If A is this, in first case it was R related. Now we say it's related to B. So then there exists say T and T dash in S such that this T of A, it should map LB, LA onto LB and LB onto LA actually. So that one or later, okay. Yes. Now here it's TA is equal to B and T dash B is equal to A. And define define left translation. Now let's define left translation. Define root T dash from S to S by root T dash of X is equal to T dash X. Then you will see that this maps then this row T dash, it maps B onto T dash B, which is equal to T dash B is equal to A. It maps B onto A, and you will see that and we then also this row T dash maps LB onto LA. So you can easily verify this. It maps LB onto LA. Now important is that this row S and row T dash, they are actually inverse of each other when restricted to LA and LB. So their composition, we have to see their composition actually. So we'll see that their composition is identity. Their composition is actually this it's left translation, and so row S and row of so also you can see that in case in the previous case that this whenever A, B, they are related, so that there is S and S dash such that AS is equal to B and BS dash is equal to A. Then if we have defined a map row S of X is equal to XS. So if we define row S dash of X is equal to XS dash, then this will map B onto A, and this row S dash, you can see it maps LB onto LA. So this row T dash actually it maps it does not map LB, it maps RB actually. It maps RB onto RA. Okay, it's to develop that map. So whenever two elements A and B, they are L related, then this row T dash, which is defined by row T dash of X is equal to T dash of X, it maps RB onto RA. And if you define here row T, rho t. If you define rho t of x is equal to tx, rho t dash of x equal to t dash of x, t dash x, and if you define rho t of x equal to tx, then this is also a left translation. It will map Ra onto Rb, and rho t dash will map Rb onto Ra. As we have seen that this rho s it maps La onto Lb. Then you can see this rho s dash, it will map Lb onto La. So if A and B are related to each other, then there is a connection of this map with La and Lb. A and B are related, but its connection is with La and Lb. In a way that it maps this rho s, it maps La onto Lb, and rho s dash it maps Lb onto La. And on the other way, if on the other side, if A and B are L related, then this then it has a relation with R. Then it's related to the R classes actually in the way that this map rho t, it maps Ra onto Rb, and rho t dash it maps Rb onto Ra. So these are actually they are actually four maps. So whenever A and B are related, we have two maps, rho s and rho s dash, and whenever A and B are related, then we have again two maps. One is rho t and rho t dash. So let's discuss this map actually, rho s and rho s dash. We will see that they are inverses of each other when restricted to La. We will see that this actually rho s dash. What's rho s? Rho s maps La onto Lb, and rho s dash it maps Lb onto La. So what's the composition? This is rho s dash. It's a composition from rho s dash. Rho s dash maps Lb onto La. So first rho s, it's La to Lb, and then rho b. It's a map from La to La. And we will see that this map is actually the identity map. That means rho s is inverse of rho s dash and restricted to La. And similarly, we will see that rho s dash rho s, it's a map from Lb to Lb, and this is also an identity map. So that's very simple. Let's choose any element here. Let x belongs to La. This means x comma a, they are L related. So that means their x to u and v such that they are L related. Also means that ux is equal to a and va is equal to x. Okay. So let's try to find the image rho s dash of x. What's x? X is equal to va. It's va of rho s dash. Let's first apply rho s. What's rho s of this? It's equal to s times it's rho s of va. Rho s of va. Okay. It's equal to s va s dash. Let's see. So first I apply rho s of va is equal to vas. Actually rho s of x equal to xs. That's the definition. It's a right translation. Rho s and rho s dash is also a right translation. Rho t and rho t dash, they are left translations. That's equal to. What's as? It's actually b. V, B, S dash. And what's BS dash? That's again equal to A. It's VA. And what's VA? It's equal to X. So rho S dash of X equal to X, which means that rho S its identity. Similarly, rho S dash rho S of x equal to x for all x belongs to LB. So in other words, they are inverse of each other when restricted to LA and LB respectively. They are inverses of E. They are bijection mappings actually. They are actually bijection mappings. So they are actually bijection mappings. So this is what we call the Green's lemma actually, that we have discussed it here. Let me write this statement actually properly. That's called the Green's lemma. It states that let A and B are related. Okay, they are in R class or equivalent. Okay, and S comma S dash belongs to S, such that that's because of our relation, AS is equal to B and BS dash is equal to A. Then the translation, then the right translations, then the right translations which are rho s restricted to LA, rho s dash restricted to LB. That we have discussed it when we restricted these maps on LA and LB. They are actually bijective mappings, and they are in fact they are inverse of each other, or mutually inverse, or mutually inverse, and they are also R class preserving. R class that I will see. And we will see R class preserving. They are R class preserving. They are R class preserving. They are R class preserving. Bijection is from first it's from LA to LB, and second is from LB to LA. LA onto LB and LB onto LA respectively. So this is the Green's lemma. And dually we can define the Green's lemma from left translation. This is for right translation. And there R class preserving means that it means that whenever x is in LA, so R class preserving means that whenever x is in L class of A, then this xs is equal to then this y, which is equal to then x rho s, which is actually equal to xs translation, and this suppose the image y is the image. So x is equal to y, and that if x is equal to y, then this y s dash is equal to y s dash is equal to x. Y s dash is equal to x. So if x is in LA, then we can see this rho s of x is equal to xs. And y s dash of x is equal to x, because it's a property of the map. Whenever a and b are related, then we have as is equal to b and bs dash is equal to a. So when we try to find the image of x, when x in LA, so whenever x is in LA, so that x rho s, which is equal to x, that's equal to y, and y s dash is equal to x. Because this x is related to a means that this x is equal to, you can see this x is equal to actually x is related to a means that there is u and v in S1 such that our x is or you can say it's left they are left related. That means ua equal to x and then vx is equal to a. They are related, x and a. So which means that this x xs, okay, equal to y. If it's equal to y, then what will be ys dash, or you can say what's this then x, okay, it's s and s dash. Xs is equal to y, so xs is equal to y, and x and y is equal to, so this x s is equal to y, then this you need to show that this y s dash should be equal to x. So y s dash, what's y? What's y? Y is equal to xs. Yeah, x s s dash. Okay, x s s dash. But what's x? X equal to ua. It's x equal to ua. So it's u a s s dash. And this u, what's as? As is equal to b. That's already defined. B s dash. And u term is b s dash. B s dash is equal to a. It's ua. And ua is again equal to x. So y s dash is equal to x. X s is equal to y. If I assume that the image of x under right translation is y, then y s dash is equal to x. So which means that they are actually R related. They belong to R. So whenever a and b, they are R related, and if we define the right translation by rho s of x equal to xs, then these x and y, then these x and its image, they are also R related. They are also R related. That means this rho s restricted to LA, it's R preserving. Because x should be in LA. It's R preserving. Okay, this is the Green's lemma. When they are restricted to LA, they are actually bijections and inverse of each other, rho s and rho s dash, and they are also R preserving. They are also R preserving. So in the next lemma, we will see that if A and B are D equivalent, or they are in same D class, if A and B are D equivalent means they are in same D class. In a semigroup S, then the cardinality of H class of A is same as cardinality of H class of B. There is a bijection between HA and HB. There is bijection. Proof. Now A and B are D related. Okay, A and B are D related. So since AB belongs to D class, which is equal to L composition R, so that means there is C in S such that A comma C belongs to L and C comma B belongs to R, because they are D related. Now since AC, from these two A and C, they are F related, and from this pair we can find S and S dash, T and T dash. For this we can find S and S dash such that let's write here first R, because they commute with each other, so there's no problem choosing R composition because we are dealing with actually R. Right translation first. Okay, so A and C, they are R related, means that AS is equal to C and AS is equal to C and C S dash is equal to A. C S dash is equal to A. And for this, it's left means the element should be left. T times C is equal to B and T dash times B is equal to C. It is equal to C. So this is it. So now let me see this since this A's are related to C, now I need to find the bijection from HA to H class of A to H class of B. So let X belongs to H class of A. Okay, X belongs to, so A and C are related. A and C are related to each other. Okay, A and C are related to each other. Okay, and X in HA means actually HA is equal to LA intersection or A. It's very simple. So this X is also L related. L related means that whenever A and C are related to each other, then the images of X, this is what's the image of X? That's actually XS. The X and XS, they are, then X and XS, they are also R related. So then X is R related to XS because it's R preserving when restricted to LA. So whenever A and C are related to each other, then X and XS, they are related to each other when the map is restricted to LA. Actually. So X is in HA and X. This means that X is R related to A and R related to A. So X is R related to A means that since R relation is right concurrence, so that means XS it belongs to LAS. It belongs to LAS. And what's AS? AS is equal to C, so that's equal to LC. That's equal to LC. XS belongs to LC. XS belongs to LC. So XS also belongs to RX, XS, and this XS, it also belongs to RX. XS belongs to LC and it also belongs to RX. But this RX, X and X is related to A, so it's same as RA. It's same as RA, and RA is related to C, so it's same as RC. A is related to C. Okay, that's here. A is related to C. So you can easily verify these things. Here, look at this. X belongs to HA. HA is equal to LA intersection RA. Now here A is related to A is